it's my pleasure to introduce to you the team from the University of Maryland University College.
Good morning and welcome to our presentation on vehicle delivery optimization. We're from the University of Maryland University College. Just as a brief introduction, I'm Rachel, I'm the team lead. Our data visualization and insights contributors are Vinod and Kim. On the modeling and coding side, we have Jacob and Conrad, who unfortunately can't be with us today. Our team coaches are Dr. Harans, Dr. Node, and Dr. Gorcheva. Fun fact, we worked remotely on this project, so this conference is the first time we're actually getting to meet in person. Just a quick overview of the topics we'll be covering. We'll briefly describe the business problem. We'll lay out our methodology and approach, highlight any data insights and trends we discovered. We'll dive into our static non-AV model we created. Out of the 4 types of networks, this was the only one we were able to produce output for. And we'll discuss several improvement opportunities. I'll pass the mic to Vinod.
Hello everyone, my name is Vinod. The primary business problem that we focus to solve here is to cut down the shipping cost, cut down the operational cost, and improve the lead time delivery for the 4 network scenarios: static and dynamic routing, AVs and non-AVs. This picture representation summarizes the primary scope of our analysis, like efficient route. We identify the plan for the efficient route for the dealer routing, and whether to keep the VDC open or closed. Shipping decision whether to ship direct to the dealer or do the milk run delivery, and delivery decision whether to wait or ship as soon as possible, and determine the optimal transport mode, whether it is AV, truck, or railroad, and when to use the AVs or the dynamic routing. And also, these are all the business constraints that we account as part of our model development. We classify the business constraint into 3 categories, like logistical constraints, like AVs cannot drive more than 300 miles, and the monetary constraints, like cost involved in setting up the VDC, the vehicle cost, like shipping cost, delivery cost, etc. The physical constraints, like no dealership access to the railroad. I'm passing on to Kim to talk about the methodology and approach.
So our team applied the agile approach to tackle the project, and our goal for the first iteration was to produce a minimal viable product of a working model. And we also utilized the CRISP DM method. It's a cross-industry standard for data mining. For our visualization team, we utilize Tableau Prep to understand, cleanse, and transform our data. So with such large data set, we also utilize Tableau Extract to reduce the data size, and so it can improve, visualization performance in Tableau Desktop. So for data modeling, we use SQL Server to query and perform data engineering in preparation for our modeling in Python. So as part of data understanding, we comparing both the historic and the problem set at first. Some insights that we found are plants and dealership networks stay consistent with new dealership added over the years. And in 2013 and 14, we have higher number of vehicle than 11 and 12 or 15 and 16. So let's now dive into the distribution of each plant. So plant F and R all locate close to each other in their Midwest region. FF served mainly in the US. Plant RO has very similar distribution, and it is increasing its footprint in Mexico and the West Coast. 3A located in the Southwest region, and it has the widest network of dealership. And among all the plants, so last one is SO, is located in Mexico and has the most distribution there. And it also has the highest number of vehicles. So we pay close attention to this trend to kind of gauge for new VDC location in the future. Here we're diving into the more of the historic data set. So here you see the comparison of the transportation, and we see that for the VDC, that close to plants used to like train, but they're not much of them you can see. But the majority of them use trucks. So seeing this trend, we simplify our model just to have trucks for VDC shipments. So here we have the lead time comparison. There's a slight increase in lead time in 13 and 14, and in particular, the bin 15 that have 15 days are highlighted there. So up next, we are comparing the VDC and vehicle in both data set. Here we see that in 2013 and 14, there's 6 new VDCs, and also in 13 and 14, highlighted at the corner over there, those 3 VDCs that were closed. We also see another interesting area is 2 VDC with significantly less volume at the bottom, had a high increase in vehicle volume. Located in the same area as the 2 that have a high vehicle volume. And here we see a direct correlation between vehicle overflow capacity and total cost. So of course, plants have higher cost, capacity, and overflow, and there was an increase in overflow in 13 and 14, and the overflow trend seemed to shift from VDCs to plants, and this is an interesting area since in 13 and 14 we used to like plant to store vehicle. Now let's just focus on just the VDCs. You can see that there's no plant in the West Coast in 13 and 14, so there was a significantly increase in the overflow on the bottom left graph. So this trend is kind of help us recommending new VDC later on in the process. So here we see that the majority of the vehicles shipped using direct route method, which was from plant to VDC to dealer. So seeing this trend, our first model only apply the direct route method. We also see an increase in milk run route in data set 2 and significantly less undelivered vehicle. So on the bottom graph is the shipment bins, and the majority of the shipments fall under 1,000 miles. And of course, the higher the shipment, the higher the cost. Now I'm passing the mic to Jack to dive into our model.
Good morning, everyone. So to implement the static non-AV model, we decided to go with a greedy algorithm approach with the primary focus of minimizing the distance traveled from the plant to the dealership. To support the model creation in Python, we loaded all of the historical data into an SQL database. This allowed for custom queries to be written and easier extraction of the data. It also supported us to easily calculate the distance between plant, VDCs, and dealers and store that information. So we initially approached this problem with an optimization approach. We ran into issues with some of the calculations, and so we decided to go back to a rules-based approach. Some of the rules that we implemented with this was only shipping full shipments, only calculating the network once per day, so we ignored any shipments, the minutes and seconds, and only looking at the current day's inventory and not utilizing the 2-day look ahead. So the flow of our model was to look at all the incoming vehicles every day into the plants and calculate the VDC to dealer distances and shipments. We then looked at all the plant and dealer combos, processed all the incoming shipments to the plants and VDCs, calculated all the VDC overflows, created the full loads by train or truck, updated the plant inventories, processed the outgoing VDC shipments, and updated the VDC inventories. So we ran the model twice just so we would have a comparison of results. The first time we ran the model, it executed in a little over 3 days. The second time was a little over 2 days. Our model had a total cost of a little over $2.4 billion for the 2-year period, with an average lead time of 25 days per car. Now I'll pass the mic back to Kim.
So yeah, now we dive into the analytic of our output. As mentioned earlier, our model only had truck shipments for VDC. And here is our lead time analysis with an average of a little below 25 days. And this reason was because we wait for full load shipment of 10 or 20. However, most of our shipment fall below 30 days. Here you can see highlighted in blue are lead time lower than 15 days, and highlight in orange are lead time higher than 15 days. So seeing this trend, our next iteration is to modify full load shipment logic so we can reduce our lead time. So this visualization shows a correlation in vehicle volume and overflow. Our model did not utilize plant capacity to store vehicle. As the result, you can see our plant did not have any overflow. So focus on just a VDC, there's a direct correlation in overflow. However, the capacity does not have the same correlation, or the blue graph on top. It's because we did not utilize many VDC. So our potential improvement here will be to utilize more plants capacity and VDCs that close by. So for simplification, as mentioned, we focus on just static shipment from plant to VDC and to dealer. So the bottom chart shows our distance bins, and which is blue are the shipments within 500 miles. The green show the shipment between 500 and 1,000, and the orange shows shipments above 1,000 miles. So we will apply milk run route and add VDC later on to help reduce the leg distance. So that concludes the analysis of our output. I'm going to pass the mic to Rachel to go over the improvement opportunities.
All right. As for VDC policies, while our VDC costs don't account for any specific new network locations, our recommendations are based on projected regional demand. We propose adding 2 new VDCs with capacity levels of 800 to areas of the South in Alabama and in the West in Utah. This would be a $2 million investment. This map shows states with the highest inflow in blue, while those with the highest outflow in red. Our recommendations are based on 8 years of tracking data by the North American Moving Services. By adding VDCs in Utah and Alabama, this would position them in centralized locations that are in regions experiencing the greatest population growth. As for closing VDCs, we recommend removing 3 of them, namely WH, QW, and WK, which are in northeastern United States and are in regions of lower projected population growth. These VDCs geographic locations, have the exact same coordinates as VH, CW, and VW. These VDCs were taken out of GM's network in 2013 and 14, and our output shows that no deliveries were made to these distribution centers. By removing these from the list of existing locations, it would save $876,000 every 2 years, and the cost differential between investing in 2 new VDCs and closing 3 is $1.1 million. So we identified 6 key areas for model improvement opportunities. First, by recalculating our VDC cost, if we consider reducing capacity levels at plants and our most underutilized VDCs, and remove the 3 empty VDCs from our network, we could save $25.4 million. We'd like to deliver more vehicles via partial load. Currently, we only ship full loads, and currently in our model, 3.87% of vehicles don't make it to the dealer. We could improve by incorporating milk run deliveries and consider shipping to nearby VDCs based on capacity levels to avoid overflow cost. We'd really like to reduce our lead time and get it down to less than 2 weeks. And if we did this, we could save $201.9 million. We could enhance our model by increasing our outlook and forecast up to 2 days in advance. And if we run our model on a cluster environment and implement multi-core processing, we could improve its runtime with getting it down to our goal of less than a day. And by refining our model and implementing these improvement opportunities, we could reduce our total network cost by 9.4%. And with further testing, this could be improved even more. So we'd really like to thank GM and INFORMS for the opportunity to conduct this research. Thank you so much for attending our presentation, and we'd be happy to take your questions.